So welcome to this lecture in Electromagnetic Experiments. It's a short appendix to Chapter 6 with all the magnetic fields in materials. Now I'm going to show you, this is a very strong magnet. It's just a permanent magnet, like the ones you stick on your fridge, except it's much stronger. Beneath it is a superconductor. It's one of the cuprate superconductors. If you cool it down with a magnet nearby, the field lines freeze into the superconductor. This means that if you try to move the electromagnet, Lorentz law will make sure that it doesn't move, because you can excite any current which will stay there for any given amount of time, since it's a superconductor. So as you can see now, well, this is a funny phenomenon. It's really, you have to apply quite a lot of force. You can apply quite a lot of force and it doesn't move. I can actually move the superconductor. And as you can see, I can spin it, because then I don't change the magnetic field lines. I don't change the flux in any sense. But I can't really, for example, lift it. Let's see, this is probably cold, but what the hell? There you go. I can lift it off, but the superconductor now has currents running within. So when I take it back, it remembers. That's pretty neat. Okay. But aside from that fact, this is the more spectacular experiment. But I could also show you the fact that it's also a perfect diamagnet. If you freeze the superconductor before you apply any magnetic field, it doesn't have any memory of any magnetic fields. So when I insert the magnet, it tries to make a current that reduces the flux again. We'll get to this, but this is Lorentz law. I think you learned it, at least briefly in high school. If you try to insert a magnetic field, change the magnetic flux in any sense, then you get a force. For example, if you move a current through a magnetic field and the flux changes, like in an electromotor essentially. So let's try if we can heat it and then freeze it again. Well, if someone wants to try and touch it, they can do that now. I guess we don't have time for everyone, but... Jeg vet hvor den skal stå. Den kald, da. The suggestion was to lick the magnet, which is not a good idea. Yeah, so you actually managed to bend it a bit, which means that probably some part of the superconductor is not superconducting anymore, but as it heats up, you see the nitrogen boils away. Liquid nitrogen boils at minus 196 Celsius, and the superconductor becomes superconducting just above that temperature. Ta den helt bort og sette den på igjen. Yeah, funny. Right, so I'll just take this one off. Right, and now it has to heat up again. So I think we'll just start the lectures for a bit, and then as it heats up, we'll cool it down again without the magnet present. And then it's going to be a perfect diamagnet. Okay? So, all right. So the topic of this week, and as we move along, is going to be the general case of electrodynamics, where we have time dependence. We keep all the terms unless we see some reason that we can do an approximation. And well, this is the general case. It's the full theory. And just to remind you the equations. The Gauss law, the sources of the electric field. equivalently for the magnetic field, except no one has ever found a magnetic dipole. This is the law of induction, which is basically what we did here, or something like that. It's called Faraday's law. There we go. That's called Ampere's law. By the way, I forgot something. We had a meeting with the reference group last week. Any questions? Okay. This thing? Oh, well. Yeah, we had a group with we had a meeting with the reference group. I wanted to discuss this with you. Basically, I think the reference group was pretty much happy about the course. There was 2 comments on the examples in the course. Someone said that there's just a perfect amount of examples, and someone said that there's not enough examples. So I think we have to conclude that I can't make everyone happy, but it's a theory course, so we must, we have to do some theory, which means that we don't have a lot of time for examples all the time. Also, there was a question which I think is important. Are the chapters that we don't spend a lot of time on, are they important on the exam, like the magnetic fields in materials? We only use like 1.5 lecture hours on that, and my comment to that is that I consider the electrostatics and magnetostatics as required knowledge, more or less, to be able to deal with the general case, which we're moving on to now. So it's no less important than any later chapters. And of course you might get exam problems from anything in the course, but I think those parts just take less time to lecture. I think that's the appropriate reply. Also the exercises, someone said that they're a lot of work, and this is true. I mean, they're not, I mean, you don't necessarily have to do all the problems, because it's supposed to be more than enough problems so you can do calculations until you drop dead, so to speak. But this is so that if someone is very interested, they could do a lot of exercises to learn the course very well. And also then that the exam problems will be easier in the sense that there will be less calculations required than some of the hard exercise problems. And this is simply because there's limited time on the exam. And also it's not primarily a math exam, of course. On the midterm course, there was some comments that people didn't really know what to expect and what to write because they hadn't done it before. But I haven't done it before either, so there's that makes 1 plus many of us. I also remind you that I put a very specific list of what do you get points on, so to speak, on the midterm project, so that you should really know what to put in the report to get the full score. So you should be able to figure that out by reading the text carefully. It seems that the programming language is popular with the students, and one of the reference group members even said that the project was fun, so I hope there's more than one of you who thinks that it's fun. And the group suggested that the physics part could be a bit more challenging, but the programming should be not too hard if we do this next year. So are there any comments from any of you on this reference group meeting? I'd be interested to hear if you have anything. Okay, then we'll check if the superconductor is warm enough. How do you tell? There you go. Now it's just a piece of something. See, I can just move it around, there's no force. Okay. And now I'm going to cool it down, and it's not going to remember any magnetic field because this guy is going to be far away. this is far away in this context. And when it stops boiling, it's at minus 196. Right, I think it's ready. And now I can really feel that it doesn't want to stay on top here anymore. I can't leave it there. So if we can move it, I'm not sure if we can, but I think it's too heavy. There you go, I didn't touch it. You see that? It gets cold pretty quickly. So this is the perfect diamagnet. Now there's no magnetic field inside. The superconductor sets up currents, which will then take away the field that this guy tries to impose inside the superconductor. And it's strong enough that I can move it around without touching the superconductor. So I said that diamagnetism is a weak effect. This is of course not quite always the case. You got it on the camera? Great. Okay, so I think we have some liquid nitrogen left. So if someone wants to play with it in the break, I think you can allow that if you promise to be careful. All right. Any questions on diamagnetism? By the way, if you're really interested in examples of where to use electromagnetism, I think Chapter 7 is a great place because you get all the theory from electromotors, well, pretty much any sort of well, generators, all that kind of practical stuff which you see around, electromagnets we discussed before, of course. Right. Now, and these, let's get back to the theory. Yeah, we have the full Maxwell equations, and from now on we're not going to just say, okay, in the magnetostatic regime we just said that we take away any electric field equations, we take away any time dependence and charges, for example. But now we're not going to take away anything unless we know that there's a reason to take it away. And we're going to discuss various subjects like radiation, which is a very important topic. This theory is essential, for example, to optics. If you want to do optics in a sense, then this course is probably more important than the optics course. And I think we might have some examples on that later. But first of all, to recap the theory, we needed the constitutive relations to solve the Maxwell equations. And what is a constitutive relation, if you don't remember? Well, that's the thing, the mathematical connection from D to E. And similarly, from B to H. And as we discussed before, these are very complex in general, complicated, you might say, even though they might be complex also in the sense that the dielectric constant, for example, can be a complex number. And because of the fact that these relations are so complicated in general, and also because there's a lot of applications where linear and homogeneous materials are important, we're going to assume the following, on most occasions at least. Unless specified, this is what you're going to assume. You're going to assume linear materials. We're going to assume isotropic materials. And homogeneous materials. And can anyone remind us what's linear mean? What does it mean? There's no one? Yeah, there's no quadratic or even higher order terms. Yeah. Okay, and isotropic, any volunteers? Exactly. And homogeneous? Yeah. So if I'm moving around inside the material, it doesn't change anything. If I look in a different direction, it looks the same. And if I insert a stronger field, then I just get twice as much D back from the same E, so to speak. And then we can write this in the following way. The D field is proportional to the E field with a proportionality constant, epsilon r, and epsilon 0, which is essentially a bunch of units. And epsilon r tells us how much D field do we get for some amount of E field. And this is a material constant. So if I'm at, let's say, boundaries between two materials, this changes. And then we get some jumps in the field, which are this is connected to the boundary conditions, of course, and I'll remind you about those in a few minutes. Equivalently, we can write that the B field is proportional to the H field and linear in the same fashion. And just to remind you, the polarization is epsilon naught chi E E. So this is how much polarization does you get out of the material when you insert some E field. And in an analogous fashion, you get magnetization. There's no mu here, actually. Okay, it's chi m, then h. And just to remind you, the epsilon r and mu r are connected to the chi's in the following way. There you go. So this is the, well, typically if you have, let's say, a piece of glass, you're interested in the optical properties. Well, this one is equal to 1, essentially. And so this guy is the material constant, which defines how light behaves inside the glass, for example. Just as an example of that. Okay. Also, just to note that if you don't have an isotropic medium, this is an optics example, really. If this is a rank 2 tensor, well then the speed of light is going to be different in different directions. This means you can make things like quarter wave plates and half wave plates, but you'll discuss those in the optics course, so for now we'll just forget that. Another essential ingredient to the theory is the Lorentz Force Law. This is Force Law. So it's the force from the electric field plus the force from the magnetic field. And you have to move around to get the magnetic field, to get any force out of that. So this is essentially what connects the electromagnetic stuff, which you see in the 4 equations over there, to the Newton's law, Newton's second law essentially. So this is, well, mass times acceleration, as you all know from before. Okay. And now to remind you about the boundary conditions, what those are in the time-dependent case and how you derive them. I'm just going to get some more space and then we're going to get those up on the blackboard. Okay. What we're looking at now is the interface between two media. This is boundary conditions, and I'm going to keep using this abbreviation, so get used to it. Okay, so I'm looking at some surface. On each side of the surface there's a different medium. I call them 1 and 2. It could be, let's say, glass and air, or some such. Let's see. I'm just going to draw these 2 sketches because I'm going to use them later. Like this. So it's a normal vector. This is what it looks like from the side. And we have the following 4 boundary conditions in the general electrodynamic case. And this comes from the Gauss Law. This is derived equivalently to the electrostatic case because the Gauss Law looks the same in electrostatics as in electrodynamics. And just to finish it off, this is the same as here, right? You derive it in the same fashion, and that is the following. You integrate over some small pillbox. So now you integrate over this small, any of the 2 Gauss laws, so to speak. You integrate them over this small pillbox. You set the height to go to 0, and then you get the top boundary equation or the bottom boundary equation. Boundary condition. And we did that before, so I'm not going to go through it again. Okay, so that's a known result. The equations are the same as in the static case. So what are the 2 remaining boundary conditions, you might ask? Well, this comes from Faraday law, of course. And equivalently, for the Ampere law, you can derive a boundary condition in the same fashion. The source of this boundary condition is, of course, the Ampere law. And the K is the so-called surface current. Now I'm going to, before I derive them, I might say that, well, in mathematics, what are you concerned, what's your primary concern? Well, that's the equations. So what's the mathematical properties of the Laplace equation, the Poisson equation, and so on? Does a solution exist? These kind of things. In physics, we're actually more concerned about the boundary conditions, because, well, I could write down a general form solution of the Poisson equation, for example, but it won't be very interesting because it doesn't connect to the physics, so to speak. Well, what do you need then to get to the physics? Well, that's the boundaries in a lot of contexts. You put, for example, some curved glass, then you have a lens. Typical example from optics. You put a magnet on the table and you have some fun, so that the mu's and the epsilons are not continuous anymore. There are jumps in the mu's and the epsilons, the permittivity and the permeability. So this is where the physics lie, in the boundaries. And these give you the boundary conditions to solve the equations, to write down the specific solution for your problem. So this is the physics of it. That's the mathematics is in the four equations to the left, and the physics is in the four equations to the right, so to speak. And now, 1 and 3, we derived those before. I'm going to do number 4. And then you'll realize that this is the same, because the Faraday and Ampere law looks the same, except that there's a J term in only one of them. The source term, the current. Okay, so first of all, I'm going to integrate over a small loop here. Actually, I'm going to integrate, first of all, I'm going to integrate over this surface. And this little loop has length L, like this, which is finite for now. And it has a height h, but I'm going to let the h go to 0. This is essential. So if something sort of happens here, it's only going to be at the surface, because I'm going to approach it by reducing the h to 0 around but keeping the surface inside the loop at all times. Okay, so first of all, I integrate over this little surface, and I take the left-hand side first. There you go. But now, of course, I'm interested in the H field itself. How does that behave? So I'm going to use Stokes theorem, or the so-called curl theorem, if you like. So I'm integrating over the closed loop. And this is, of course, equal to the parallel component times the length. Let's see. So that's the left-hand side of the Ampere law. This is the parallel component. So if I have, let's say, I'm going to draw this a bit away because otherwise there's no room. This is H. The perpendicular component does not contribute because those terms would, that component is only going to contribute here and here, but as H will go to 0, those terms are going to be 0, not going to contribute in the end. So it's only the parallel component. And then on the right-hand side of the Ampere law, you have, first of all, the integral over the current flowing through the surface. And then the surface integral over the time derivative of the d field. However, as the area goes to 0, then this term is going to be 0 as well, because there's simply no area left. Now you can see that I'm actually stuck with the same as I had in the magnetostatic case. And that's that you essentially have the surface current times the length of the loop. And if I combine the two of these, then I'm going to be stuck with the same boundary condition as I found in magnetostatics. Because in the end, the time-dependent term didn't contribute. Only the surface that was really stuck to the surface was able to contribute anyway. And you can use the same argument for this equation, except there's no magnetic charge, so there's no magnetic current. So this term is equal to 0 for the electrostatic case. You just change this to 0 and the h to e, then you got the full derivation right here. Okay. Those were the boundary conditions. And now we're moving on to the continuity equation. And now I'm going to start out by looking at, first of all, this equation, and second of all, this equation. I'm going to start off by taking the gradient of the lower equation here. Start out with the left-hand side. The gradient of curl is 0. That was easy. Now, first of all, you get the gradient of the current. And the gradient is essentially partial derivatives. And this is a partial derivative, and those commute. Let's see. So I take the gradient of the d field as well. This now, of course, is equal to rho. And this was all equal to 0. So in the end, I end up with a continuity equation, which you probably know from fluid mechanics. And in the in classical electrodynamics, this is equivalent to charge conservation. And I think we discussed that at one of the previous lectures. And we all discussed the Gauss Law. This one. This was experimentally verified by, well, suggested, I might say, by Coulomb. You all know the Coulomb's law between two point charges. They look like the gravitation law. And from this you can show this Gauss law. We also discussed that, well, if you have currents running around, then you get magnetic fields. This was the discovery of Ørsted in 1820 or so. And that's the magnetostatic term in this equation, right? The H field stems from the current. Now, if you look at this derivation of the continuity equation, you'll notice that I used this term here, which wasn't, well, this term you might say, the time derivative of the displacement field. This was not originally in the Ampere law because Ampere was only considering magnetostatics. But Maxwell realized this means that charge is not conserved, and well, actually that's not the historical reason, but as you can see, it leads to mathematical inconsistencies. Actually, Maxwell believed that there was something called the ether, which light was moving through, a substance which you couldn't really see or touch, but which you sort of needed to get electromagnetic radiation, that is light. However, we all know that the ether does not exist, which was experimentally verified by Michelson Morley in the early 1900s or so, maybe 1890s. So now Maxwell actually fixed the Ampere law by adding this term. Yeah, and this is actually a very nice symmetry, right? If you, let's say, we don't have any currents right now, we take that term away, then you have the following equations. And if we stick to the vacuum for the time being, no, plus. Okay, so as you can see, if you have a time-dependent B field, I'm going to get an E field out of that. If I have, let's say, a magnetic wire, shake it, an electric field shows up as well. Equivalently, if I have a time-dependent electric field, let's say I move a charge around, well, then there's a magnetic field that shows up. This is a very nice symmetry. If you have one of those fields, you can excite the other, so to speak, by changing it with respect to time. And so I think Maxwell was pretty happy about himself when he found out about this. But well, that's this is sort of the idea why. And as charge conservation has always, there's no violation of charge conservation ever observed, even in astrophysics or particle physics experiments. So we really believe that charge is conserved in the universe in the same way as energy is and several other quantities. Okay, so we're going to discuss this term a bit later, but now all the rest of Maxwell equations should be clear from where did it come from the experiments. It's the Coulomb law, the Ampere law, no, sorry, the Biot-Savart experiments. And Maxwell sort of put in this term to get the continuity equation right, we might say. And now what's left is the Faraday experiments, which gave us induction. And we're going to look at that after I show you how the potentials change in electrodynamics. All right, we call this V, the scalar potential, and A, the vector potential. And we use these because they gave us nicer expressions for calculating the E field and the B field from, let's say, a current distribution or a charge distribution. We could show that in that case, electrostatics and magnetostatics is equivalent to solving the Poisson equation, which is not the worst equation around, let's say. But now, as we move on to electrodynamics with time dependence, there's a new term that shows up. Let's see. So, okay. First of all, the definition. So we assume that Maxwell equations is the fundamental, let's say, set of rules that governs electrodynamics. And then we define our scalar potential and vector potential out from those equations. And then we find the following. This term is new now, right? Now, where does this come from? Well, the B equation is the same as before, but now when we went to the electrodynamic case, we added this term here. And for that reason, we need the dt, or the time derivative of A in the E field. So as you now can see, we can't just choose the gauge of A without thinking about how does it affect V. And we're going to discuss that in chapter, what is it, 10 or something? So you have to be a bit more careful now if you want to twiddle with the A and the V. There's still some freedom of choice left, but you have to be more careful as they couple because of the time dependence. And just to show where this comes from, we just look at the Faraday law. The curl of the E field, I just insert the potential expression first. This is of course equal to the following. The curl of a gradient is 0, so it's dt curl of A. But this is of course just the magnetic field. So as you can see, this new definition is in fact consistent with Faraday's law, and we're done. But however, for the B field, there's no new term in well, this equation. There's still no magnetic charge around, so this means that this equation doesn't change when we move on to electrodynamics. And I think we take a break now, so if someone wants to come and play, then there you go. As you can see, the superconductor can induce any sufficiently strong current to oppose the change in flux when you try to move the magnet. Oops. And it has perfect memory. There you go. Of course, you need a very strong magnet to get this strong effect. So if you put this magnet near to any credit card or some such, it's not a credit card anymore. You can also, this wobble is probably from the magnet not being perfectly rotationally symmetric, because in that case the magnet will try to resist that change.